Introduction to wavelets. The wavelet transform is among widely used technique for extracting features from biomedical other signals as radar signal processing, speech signal processing. The wavelet transform tries to mitigate the limitations of the short time Fourier transform, whatever we discussed in a previous. Means time localization is not possible, time frequency localization is not possible, and it do a better job. It starts by defining special basis functions called mother wavelets. When you are using wavelet transform, we have to define the mother wavelets just like basis functions what you are going to define for the Fourier series like that. Mother wavelets are not restricted to a single family of functions. Example, in Fourier series, we thought about Fourier transform, whatever it may be, we thought about periodic functions, only the basis functions. But here in wavelet transform, there is no such a restriction. In addition, the basic functions have both temporal and frequency components. This allows us to generate a series of variable sized wavelet functions. Whatever the problem, we saw that in a short time Fourier transform, there is a facility to have variable sized window functioning. Each has a share of the time frequency spectrum. So, wavelet transform computation is unique in three aspects. It can be used to represent a transient signal structures that are quite common in biomedical signal processing. The window width is varied from every signal spectra component. For optimized resolution is possible. The signal is decomposed into wavelets. Scaling can cause either dilation or compression of a signal, thus generating opportunities for multiple applications of the wavelet transform. Dilated version could be cascaded in order to develop newer concepts such as scattering transforms or some similar deep belief networks for signal decomposition, whereas compression versions could be used in sensing technologies. The wavelet transform has a good frequency and a poor time resolution at low frequencies and vice versa. Those can be shown here. So, in short time Fourier transform, whatever it may be the signal details, we can have a fixed time window so that we are going to get a fixed frequency resolutions. But in a wavelet transform, here the time slot going to be having more length, we are having less frequency. That means for capturing low frequency components, we can have a frequency resolution, and further you can do that time resolution can be reduced and frequency resolution can be improved, and further we can reduce the time resolution. That means we are going to have that frequency axis can be increased. There is no fixed time versus frequency representation like a short time Fourier transform. For a fixed window size, we are going to have a frequency resolutions, so we can adjust the window size, either required time length and required time length as short and long. By this way, we can conclude that wavelet transform has a time frequency resolution. Simple example here. Simple example: good frequency resolution, bad time resolution. Time axis increases, we are not able to localize the time. That means a bad time resolution. Good time resolution means we are going to observe very short localized time, but frequency components may be multiple frequencies, bad time resolution. So Heisenberg has given that time frequency resolution going to be fixed, constant, just like a gain bandwidth product. Either you are increasing the time frequency resolution, you are losing time resolution. You are increasing the time resolution, you are losing the frequency resolution. Depending upon the requirement and the frequency components in the given signal, you can select either time resolved section or time localization, or you can have a frequency resolved for a particular time instant. So in generally, as the time duration is more, means we are going to have a low frequency components. At low frequency, good frequency resolution, bad time resolution. So that at a very short period means high frequency components are existing. At high frequency, good time resolution, bad frequency resolution going to be happening. This is the one more discussion about wavelet transform. But what we can say here, there is a possibility to adjust the window size. Then Already we are discussing wavelet. What is the wavelet? How it looks like? Wave versus wavelet. Already you know wave from the Fourier series onwards. A wave is usually defined as an oscillating function of a time or space, such as a sinusoid. Fourier analysis is a wave analysis, especially for periodic, time invariant or stationary phenomena. A wavelet is a small wave which has its energy concentrated in time to give a tool for the analysis of transient non-stationary, or it is still has the oscillating wave-like character but also has the ability to allow simultaneous time and frequency analysis. With a flexible mathematical foundation, time varying phenomena can be observable in a wavelet. One of the example WTA's wavelet is shown here. Then some examples for wavelets are given. This is the Haar wavelet. Already we discussed that there is no any restriction in a particular family of functions. So different families of functions can be used as a wavelet. So this one is a just look like say square wave function is used as a Haar wavelet. Then WTA's 4-tap max flat wavelet going to be having different structure. Then one more is Gaussian wavelet, Moore wavelet, Mexican hat wavelet. So what are the differences existing with the wave and wavelet? Wave is usually defined as an oscillating function of a time or space, such as a sinusoid. Wavelet is a small wave which has its energy concentrated in time. That means that for a small duration only the wavelet existing. Wave can exist from minus infinite duration to plus infinite. Fourier analysis is a wave analysis, especially for periodic, time invariant or stationary phenomena. Wavelet is a tool for the analysis of transient, non-stationary, or it still has the oscillating wave-like characteristic but also has the ability to allow simultaneous time and frequency analysis, which is a flexible mathematical foundation, time varying phenomena. Then just simply what are the properties we said in 1 and 2 are going to be observable in graphical representation of your wave and wavelet. The wave oscillating with the equal amplitude over minus infinite to plus infinite and therefore having infinite energy. The wavelet having its a finite energy concentrated around a point. With this we will wind up the introductory part of wavelet transform.